Thank you for tuning in. Today we'll be covering the topic of nuclear chemistry, and this is at the FE level, and it basically stands for Radiopharmaceutical Transport Kinetics. Whatever you may understand about nuclear chemistry, it's all about the transport of certain elements in vivo, in vitro, in silico, in an enclosed system where you study the decay rate of the element as a function of time, and it's not linked to solubility, which is solubility is the rate of solubilization per unit time per Kelvin, and it's linked to the mass of water, temperature of water, and the polarity or non-polarity of the solvent. Whereas radioactivity, discussing the radioactive behavior or the radiopharmaceutical transport kinetics of different elements that are injected in vivo, in silico, in vitro, and they're being observed for the decay rate, which is very stochastic and randomized. That's part of nuclear chemistry, and what today I'll be trying to do elaborate calculations on the topic of nuclear chemistry, radiopharmaceutical transport kinetics. There's a whole master's qualification designed around this topic, and a large number of elements we know that are radioactive. They have non-radioactive isotopes as well, and then their nuclei are unstable and they split to form two nuclei. And this type of reaction is called a nuclear reaction, which is stochastic and randomized. It's quite different from a chemical reaction because chemical reactions involved the use of valence and outermost electron sharing, electron transfer, electron displacement, whereas this is strictly nuclear. And X-rays are generated from the displacement of electrons from higher to lower or lower to higher energy vibration field orbitals, whereas gamma rays are produced in and by the nuclear framework, the nuclei of the elements. And sometimes protons, neutrons, electrons, they fly out when the original nucleus divides because of the kinetic rebound and the imbalancing of the strong and the weak nuclear force. And so the particles and the energy are given out, and there are many kinds. Like there's electron capture, there's beta emission, gamma emission, alpha emission, electron capture, proton emission. All of this comes under the category of radioactivity, radioactive decay, and the breaking up process is called stochastic randomized radioactive decay. We don't know which nuclei are going to split first, but they always, it's a halving process as a function of time, as this curve would show you. It's a halving process. And the results of the measurements of the radioactive decay are always downward exponential. All life phenomena are exponential in nature. And so for particularly in this case, if we start from 400 counts, for it to reach 200 counts, it would take 2 hours. For it to halve again, it would take another. So the half-life is 2 hours. You draw the curve, and then you could do T1, T2, T3, and then you find out that T1 has to be equal to T2 equals T3, and the gap has to be constant, and that gap is the half-life. So that's how things are. So the time taken for the rate of radioactive decay to fall to half its value, is the same no matter what the original rate of decay ought to be. So this time is called half-life, and half-life is basically this. It's lambda over log natural of 2, which is lambda over 0.693, and lambda here comes from A equals minus lambda t, and that's the activity in becquerels, and that's per second, and then that's time in seconds, but this time is not the half-life. Now, this what you need to realize is that half-life is an overall summation of the physical and biological half-life. So the if what this is, it's actually the effective half-life. An effective half-life is a reciprocal summation of physical and biological half-life. So it's something like T 1 over Te equals 1 over T plus 1 over TB. So that's what it is. And now we know that, a T overall half-life is lambda 0.693, and we know that lambda is A over T. Yeah. So and then 0.693, and so this is how you can substitute and continue to manipulate the formulaic substitution. Now, the curve of a radioactive decay would always look like this, but it would never touch zero. But these differences would stay equal. So T1, T2, T3 would always be equal, and these gaps are what define the half-life and confirm the randomized stochasticity of this process. We don't know. So if you've got this lump of uranium yellow cake, we don't know which. So if you've got like 100 nuclei, every X amount of time, which is the half-life, 50 of those will break down and produce gamma emission, whatever they produce characteristically, because americium is alpha emitter. Not all elements, radioactive elements, would produce all kinds of radiation. Some are alpha gamma, some are alpha beta, some are beta gamma, some are. It depends what uranium would produce as a product of its radioactive decay. So 50 of those are bound to decay, but you don't know which one which one of those 100 would be. It could be any of those 100. So this is called randomized nature of the process, and it's stochastic in nature. Some of the very popular examples we have is carbon 14, fluorine 20, potassium 40. Now this bottom part stays the same, but it's the top one that's changing. Now my video on isotopes, isobars, isotones tells you that there are more than one kind of variation. In this particular case, isotopes have same proton numbers with varying mass numbers, nucleon numbers, but you'll have isotopes and isotones and isobars that may have different quantization in them. So we're not going to discuss isobars and isotopes at the moment. The first problem I'm going to do for you is look, problems in nuclear chemistry are very simple. Please don't be confused and don't be intimidated. You may be told that the half-life of a radioactive isotope is such and such, and you have to work out what the count rate is. Counts per minute, count rate, counts per second, count rate. So that's that. So counts per minute, counts per second, count rate. And what you need to realize is you have to calculate how the mass of a radioactive isotope will decrease as a function of time. Another kind of problem you'll come across is how to work out the half-life of a radioactive decay from a plot of counts per minute against time. So plot of counts per minute or seconds per unit time. So you have, and then you'll have to calculate. Work out the half-life of the radioactive decay. So the first question I'm wanting to is the half-life of bromine 82. Let me move to a new page. Half-life of bromine 82 is 36 hours. So effective half-life is 36 hours. Yes. And a sample of potassium bromide, which is KBr, And KBr is formed by one ion of potassium and one ion of bromium. As in aqueous solution, it would be KBr plus H2O. That would be K plus H plus OH plus Br. So that would be this. And then so you have to so when a Geiger-Müller detector has detected a count rate to be 160 counts per minute, what's the value? What will be the value of the count rate 72 hours later? So the initial so the half-life is 36 hours. The initial count rate, counts per minute, is 160, and it's asking you how long would it take for the 160 counts per minute to drop down to 72 counts per minute. How long would it take? And count rate would have fallen. So basically what you need to do is to tabulate the data first. Tabulation is extremely important to make sense of how things are, and tabulation would make your life a lot easier. So now you need to, so I've done that for you, and half-life is 36. The count rate would have fallen to half its value in 36 hours. So after 160 counts per minute at time 0. Time 1 would be 80 counts per minute, 40 counts per minute at time 2, T2. So that's 36 hours, 36 hours, 36 hours. That's that. And then so the question's asking what will be the value of the count rate at 72 hours later. So after 72 hours, it would be 40 counts per minute. So you can see it's a very unitary, the conceptual framework is very unitary. It's just common sense. After knowing the trend of half-life, you just have to provide accurate approximations, and that would do the job. And there's nothing intimidating about it. The next question I've chosen is that cesium 137 has a half-life of 30 years. You don't need to convert every half-life into seconds. Not in every case. You have to watch the mood of the question. Like what if it's about carbon dating, argon, potassium dating, then it's got to be in years, millennia even. They won't ask you to convert it into years. But if one of the units is in seconds, then it means you have to bring everything into seconds. That's quite a fine point, if I may say so. So cesium 137 isotope has a half-life of 30 years. A sample of cesium chloride here, this is radioactive. You have to put 137 to demarcate its radioactivity. So we're using 2 grams of it. So the initial mass is 2 grams. And so we have a sample of cesium-137, which has a half-life of 30 years, but it's available in form of a cesium chloride compound, and the initial mass is 2 grams. And it's asking us what will be the mass of cesium-137 chloride after 90 years. So it's basically T1, T2, T3. So the first gap. So after, it's basically 3 half-lives later. It would be, so first 30 years it would be 1 gram. Second 30 years would be 0.5 grams. The third 30 years, which is 90 years in total, it will be 0.25 grams. So at T1, T2, T3, it would be T1, T2, T3. A quarter of a gram would be left in the bottle. Now, would that be? Here's one thing I like to touch upon. Would it be? Here's a bit of, now this question doesn't address it, but if we look at 2 grams of cesium chloride, that's not 2 grams of cesium alone. It's 2 grams of cesium chloride, which is 137 grams per mole plus 35.5 grams per mole. That's 167, 172.5 grams per mole. Yes, and you're taking 2 grams of it, so that would be 2 divided by 172.5. That's 2 divided by 172.5. That's 0.0116 mole. So that's so hang on. So 137 plus 35.5, 172. But yeah, there we go. So that's 0.0116 mole of cesium chloride. If we're assuming that it's the same, if it's unimolar, then it has to be 0.116 mole of cesium as well. If we multiply it by 137 to see how much mass we get, moles. So basically, if you've got 0.116 mole of and then we multiply by the relative atomic mass, we get 1.5 mass of cesium would be 137 would be 1.6, almost 1.6 grams. Now that's 1.6 grams of cesium, and bear in mind, chlorine's not going to reduce. It's not chlorine that's going to reduce in amount of matter. It'll be, so in fact, at postgraduate level, so at FE, this would be your answer, but at postgraduate level it would be 1.6 halving to 0.8, and then halving at T3 to 0.4. So that your answer would vary at the level you're addressing it. So yeah, so please clarify that misconception. And please watch this part of the video again if you wish to revise this concept. So again, you have to look at the micromechanics of how things are, and not what the you have to have a synoptic understanding. Now, the other thing I'd like to, the other question I'd like to tackle is that the radioactive isotope of sodium decays according to the equation sodium 2411, decaying into X and N, M and N, yes. And so if we want to find out what the M and N are. So we want to know what the M and N are. Now, this is -1. That's so there's been no change here. And let me use a different marker. There's been no change here, but there's been a change of -1 here. So this would be 11 minus 11. -1 would be 12, and this one would be 24. The top one would be 24. So we would be, it's a very, very simple small question though. So the X configuration would be 2412. That would be magnesium metal. So when you do beta emission of sodium, radioactive sodium, it converts from sodium radioactive to magnesium. Yes. So there we go. Now the other question that's been bothering, and then you can find all the other examples. I mean, I'll do a few more examples, bear with me. The other examples, we've got plenty of examples. The first example would be lead. getting changed to bismuth, and an electron 0 and -1. So we want to find out what this would be. So the bottom part would be 83, and the top part would be 210. So because it's 83 minus 1 is 82, and then so again the concept is the same. You have to add and subtract, learn to add and subtract the nucleon and proton number values. Yes. The other thing I like to okay, so now a very important question. It's the question says you have strontium 90, and it's a radioactive isotope which is produced in nuclear reactors. It has a half-life of 28 years, effective half-life of 28 years. Answer the following questions about 100-gram sample of strontium 90. So the initial mass is 100 grams, and so every 28 years you'll be having so the question asks, how long would it take for 75 grams of the sample to decay? 75 grams. So the question's quite tricky. It says, how long would it take for 75 grams of sample to decay, which means how long would it take for 75 grams to evaporate or disappear? So the question, so the first half-life into it would be 28 years, and then it would bring the 100 to 50 grams. The second one, T2, would bring it to 25 grams. And if you subtract 25 from 100, that's 75 gone. So it took 56 years for it to happen. Half a century plus 6 on top. And the next question would be, how many grams would be left over after 4 half-lives? So after 4 half-lives, T3 would be 12.5. T4 would be 6.25 grams would be left over after 4 cycles. The 4th cycle would leave 6.25 grams. How many grams would be left over after 168 years? Now that's a multiple. You have to divide 168 years by 28 years. That would give you 6 cycles. So 6 cycles. So after 6 cycles, we know T4 would leave 6.25, so T5 would leave 3.125, and then T6 would leave 1.5625. So as I said earlier, it would never touch 0 or not, right? It would always keep dividing into half till it becomes minuscule and nano mass, and it keeps going into parts per billion, parts per million, parts per trillion, parts per this and that, but it would never go down to 0. Right. So that's there, and before 1 gram remains. So the next question is a bit tricky. It says, how many cycles need to elapse before 1 gram, less than 1 gram remaining? So we know 6 cycles would leave us 1.6 grams. And then how many more? So T7, I'm just continuing here. T7 would leave us 0.78125 grams. So that would be the 7th cycle would bring it below 1. Right, and then we have a question to plot the graph. Take the values. Plot the graph, this graph, and then plot it, deduce your graph, and then find out the half-life. After what length of time was the count rate 200? And answer all these very, very simple questions that we just addressed individually. So this is what Newton chemistry calculation is all about, and maybe a little bit more that I haven't covered in this video, but this is what it boils down to: counts per minute, counts per second, half-life. The other formula I didn't talk about is it can become a bit complex when they begin to introduce Avogadro's number, molar ratio, and stoichiometric proportions in there. But the most commonly used formulae are T effective equals T biological plus T physical inverse. So all of this is inversed, and then you have T half divided by equals lambda divided by log natural of 2. Then you have activity equals minus and then this particular formula, and then you have the nuclei. Sorry, hang on. So you've got this particular formula, and then you have this one, and then you have this one, and then you have the nuclear disintegration ratio. So nuclear at the beginning of time overall, and that's at the beginning. That's exp, and then exponent, and then this is the constant lambda, and then you've got the time, which is the same as that, and then you can back and forth. You can manipulate it back and forth. And the other thing I'd like to mention is that Avogadro's number. So we all know about mole, how to calculate mole. That's mass of either a compound or an element. So if it's element, then it's atomic number divided by the atomic number of that particular element. Or if it's a compound, then it's the molecular mass. So this forward slash isn't divided. It's AR or atomic number or molecular mass. Atomic number or molecular mass. Atomic mass or molecular mass. So if it's a compound, then it'll be mass divided by the atomic molecular mass. If it's mass of an element, it'll be mass divided by the atomic number. That's that. And then you have Avogadro's number, the number of particles, like number of molecules, number of atoms, number of ions. So that's so there's a specific symbol for it. Symbol is N. It's a calligraphic N, mole into Avogadro's constant. So that's that, and that the Avogadro's constant is 6.0210 to the power 23 particles per mole. So that's that. Now this is how you'll have to sometimes they might ask you to calculate the mass of they'll provide you the half-life, initial number of nuclei, the constant and the time, and then you'll have to find the mass by using this formula and putting it in there. So this would be so you'll have to use this and then plug it in, and to find out the actual number of mass of the radioactive element involved. So this is quite interesting, entertaining, and it really exercises your numerical manipulation skills quite a lot, and it gives you a lot of confidence, and it synoptically connects molar chemistry and stoichiometry and nuclear physics very, very nicely. So it's very useful for students to go ahead and try nuclear calculations, and because it has a wide range of applications in analytical and radiopharmaceutical and nuclear chemistry. One of the books I really found useful was the subdivided individualized A-level revision guide by Roger Muncaster on nuclear physics and fundamental particles. Very, very good, very useful, very effective in giving you compartmentalized knowledge on the subject of nuclear chemistry. And yes, it says physics, but it's equiproportionally applicable to chemistry as well. It's wonderful, fantastic, no comparison. I remember very few, one of the greatest books of physics is by Collins and also by Abbott. This particular book